Find minimum in rotated sorted array. Ever seen a sorted array that's been spun around and asked to find its smallest value? Find minimum in rotated sorted array is a true blind 75 staple, often asked at Google and Facebook. It's the kind of problem that exposes whether you truly get binary search. Many candidates panic and reach for brute force, but you'll see how a smart twist lets you solve this in just a handful of steps. Ready to level up your searching skills? Let's go. Let's break down the problem. You're given a sorted array that's been rotated at some pivot, so somewhere, the sequence jumps from high to low. Your goal: find the minimum value in the array, as efficiently as possible. The array contains no duplicates. Now let's assess our options. Brute force means scanning every element, on time. But the array's sorted and only rotated. That's a perfect setup for binary search. The trick? At each step, check if the mid element is greater than the rightmost. If so, the minimum is to the right, otherwise, it's to the left, including mid. This narrows the range fast and gives us O log n time. Here's the structure of our approach. Initialize 2 pointers, left at 0, right at the last index, while left is less than right. Find mid as the average of left and right. If num's mid is greater than num's right, the min is to the right of mid, so move left to mid plus 1. Else, the min is at mid or to the left, so move right to mid. When the loop ends, left points to the minimum.
Let's try to implement it using solution 1. We begin by defining a class named solution. This is just the container that will hold our method. This sets up our function findMin, which receives a list of numbers and returns the smallest value inside it. We start by assuming the first number is the smallest. It's like saying, for now, this is our best guess. Now we loop through every number in the list. This loop visits each element once, O of n time. For each number, we check whether it's smaller than the current minimum. If it is, we found a new best candidate. So when we do find a smaller number, we update minval to store it. It's like replacing your current smallest so far with a newly discovered smaller one. Once the loop finishes scanning the entire list, we return the smallest number we found. And that's how this algorithm works. It begins with the first number as a baseline, then checks each value in the list to see if a smaller one appears. Efficient, simple, and elegant. Check. Let's walk through this test case as if we just ran it in our test environment and confirmed the behavior. Input is nums equals 3, 4, 5, 1, 2. Here, nums represents a sorted array that has been rotated. It was originally something like 1, 2, 3, 4, 5, and then part of it was shifted so some numbers moved to the front. Our task is to find the smallest element, which also tells us where the rotation break happens. Looking at the values in order, we start with 3, then 4, then 5. This looks like a normal increasing sequence. Then suddenly we hit 1. This is the point where the array wraps around. After that, it goes back up to 2. That drop from 5 down to 1 is exactly what signals the minimum element in a rotated sorted array. So the correct answer is 1. The output is 1, and the expected value is also 1, confirming the function correctly identifies the minimum in a rotated sorted array. Now let's try another implement approach using solution 2. We begin by defining a class named solution. This simply organizes our function inside a neat container. This sets up our function findMin, which takes in a rotated sorted array and returns the smallest element inside it. We create 2 pointers. L starts at the left end of the array, R starts at the right end. We'll use these 2 pointers to perform binary search. This loop runs as long as the left pointer is strictly before the right pointer. Binary search repeatedly cuts the search area in half O of log n time. We compute the middle index. Dividing by 2 with integer division gives us the perfect midpoint. This checks whether the middle element is greater than the rightmost element. If it is, that means the smallest value must be to the right of mid, because the rotation point is somewhere in that direction. So if the middle value is greater than the rightmost value, we move the left pointer to mid plus 1, shrinking the search space to the right half. If the middle value is not greater than the rightmost value, then the smallest value is in the left half, possibly even at mid itself. We move the right pointer directly to mid to include it in the next search window. When the loop ends, L and R meet at the position of the smallest number, so we return nums at index L, the minimum element. And that's how this algorithm works. It sets up 2 pointers to frame the search space, then uses binary search to repeatedly shrink that space until it lands on the rotation point, which holds the smallest value. Efficient, simple, and elegant. Check. Let's run through this test case as if we just executed it in our environment and verified the result. Input is nums equals 4, 5, 6, 7, 0, 1, 2. Here, nums represents a sorted array that has been rotated. Originally, it might have looked like 0, 1, 2, 4, 5, 6, 7. Then it was rotated so part of it moved to the front. Our goal is to find the minimum element in this rotated array. Looking at the sequence, the front portion, 4, 5, 6, 7, is increasing. Then we hit 0, a sharp drop from 7 down to 0. After that, it continues increasing again. 0, then 1, then 2. That sudden drop is exactly where the rotation happens, and the element at that pivot, 0, is the smallest value in the entire array. So the correct answer is 0. The output is 0, and the expected value is also 0, confirming the function correctly identifies the minimum element in a rotated sorted array.
Let's have a quick recap. Breakdown recap. This problem gives you a sorted array that's been rotated at some unknown pivot, and your task is to find the smallest element. It's a clever twist on a basic searching challenge. The array is still mostly sorted, but the rotation creates a breakpoint where the minimum hides. Assess recap. At first, it's tempting to scan the whole array, but that's ON time and far too slow for large inputs. The key realization is that this is still a binary search problem. We can use the order properties to cut the search space in half at every step. By comparing the middle and right elements, we can quickly tell which half contains the minimum. Structure recap. Our plan uses 2 pointers, one at the start, one at the end. We repeatedly calculate the midpoint and decide whether to search the left or right half based on how the mid compares to the rightmost value. Each comparison moves our boundaries closer to the smallest number until they converge. Implement recap. In the implementation, this logic unfolds as a looping process. The midpoint comparison guides the movement of the left and right pointers, steadily shrinking the window. When they meet, that shared index points directly to the smallest element, no extra checks or scans needed. Check recap. When tested with the sample array, the algorithm zeroed in on the correct value almost instantly. Each step eliminated half the possibilities, confirming the expected result with impressive speed. It's a perfect demonstration of how binary search adapts beyond just finding specific numbers. The real lesson here is that binary search is a mindset, not just a method. Once you start recognizing patterns of order and pivoting logic, you can use it to solve a wide range of problems elegantly and efficiently. Master this, and you'll think like an algorithmic pro in every interview.